questions on the homework? Any questions on the homework? Is that just easy peasy?
Can we do part B of number 4?
Number 4, 13.4, part B?
Yeah.
Absolutely. We could actually then just transition into the next topic with that one, so. Let me draw it real quick. So, well, it'll be interesting to see how many of us did the wrong ones, right? Which one is number 4? Is it this one,
I did the one on top.
or is it this one?
I did that.
Yeah, it's that one. Because 6 is this, 5 is this, 4 is this.
Yeah, I was confused at the beginning.
No, it is, it's like, what? Which one's which? Which one did you do?
That's the wrong one.
Okay, so we're gonna do the wrong one. Because Nick's interested in this one.
What I did was.
He's doing random homework problems. Nice job, Nick.
I just didn't see the problem 13.4.
I started.
I get it, I get it. But this is the one you're interested
So I
in.
went to the bottom.
Yeah,
okay.
That's what I got.
So we're gonna do this one.
136,
If you wanna draw it and follow along, you can.
so that's how I figured it out.
It's
But it was
not-
confusing.
One of your homework problems, but it'll serve the purpose of talking about it. So it's got a full distribution over the whole thing. So this is actually 5B. I'm gonna make sure to label 13, 5B. Everyone good with this? Understand, you understand what's happening?
Yes.
Yes, we're doing a random problem. Cause it is interesting because it has the support back in here.
That's what really.
Yeah, so there's a support here called B, this is A distribution throughout the whole thing, and then a concentration on the end. $10K, a whole bunch. And 1 kip per foot distribution. And for fun, since we're gonna continue on this problem for our next topic, we're gonna make it a W 10/12. So that's the beam. Give it a real, sorry about that, give it a real call out. So we have this W 10/12. The big distribution on it and a big concentration. The first thing we're gonna do is what it asks, which says calculate the reactions A and B for the beam shown, right? Reactions. Yep. But then I'm gonna have us determine max bending, max shear, which is actually V force. And then we're gonna go for max bending stress. Yep, we're gonna push it all the way forward. Hey,
Hey,
how are you?
better.
What's your name?
You didn't even recognize it.
I'm kidding. Looks good, man.
Thank you.
Dialed in, you look fast.
Thanks. I'll take it.
Absolutely. So we're doing a random problem.
Really?
Yeah. Because it's good practice, right?
Yeah.
So first thing we want are the reactions, which was like the homework, right? How do we do that? Yeah, free body diagram first. So that means we gotta put 1 in for B. We gotta put 2 in for A. We can set AX to 0, and then we gotta solve for these by doing a moment. Yep. So when a W shape's called out, 10 by 12, what's the 12 stand for? Anyone remember? No, 10 is so it looks like this, right? It's not the length. Right, W shape looks like this, 10 is the top to bottom. And it's nominal, so we always look it up, but 12 is what? It is 12 pounds per foot. It's the weight. Second number is always the weight. So we could potentially include the weight as a load, right?
But you wanted that, right? That W10.
What?
That one's not on the original.
No, I'm making all this up, man.
Okay.
I'm adding to it. Adding to it.
Okay, you confused me because you said 30.5 and I went like, where is that at?
This is right here. And then I'm adding to it. Just because we need to start thinking whole picture here, like what the heck are we doing? We're really trying to find bending stress. How do we get there? Free body diagram. Put all the loads on, maybe include the weight of the beam, maybe not. We're gonna not include the weight of the beam. Because the weight of the beam is so small compared to the load. 1,000 pounds per foot compared to 12 pounds per foot. That's super small. So we're gonna neglect the weight of the beam. We're just gonna use the 1,000 pounds per foot and the 10,000 single load. All right. Let's find our reactions, because that's our first step. And that was like the homework. Reactions at A, reactions at B. Gina said do a moment. All right, let's do a moment. Where do you want to do the moment at?
B.
B. Moment at B. I know it's 10K times what? That's this one. Oh, we need distances. Sorry,
S B.
8 feet and 12 feet. 8 feet. And rotation about B, we're doing moment at B. Negative clockwise. And then we have to deal with this distribution. How do we do that? Concentrate it.
20.
Yep, 1 times 20, 20K. And at the halfway mark, which is 10 feet, yeah, so it's 10 feet from here. Which means it's like how far from B? 2 feet, yep. So it's gonna be 20K times 2 feet. And that rotation is positive. Comes down here, rotates around that one. Then what else? AY times 12 feet. And its rotation is negative. This does get set equal to 0. It's awesome because we're doing calculations and we're manufacturing at the same time. Can you hear it? Manufacturing going on. Robots working for us. All right, what's AY equal? Those numbers, the numbers you got, Nick? Or did you do it-
Yes.
Did you do it different?
So I did both.
Good.
I did the sum moment at A, and then I didn't like it, so then I did that one. And I
Got
didn't
it.
like that much either,
Yeah,
but it made more sense.
I'm getting 3.33,
Yeah.
repeating. And that's kips. What's a kip? Yes. So how do we get By? Yeah, just sum all the downforce, which is 20 plus 10, 30 down. And then we have an up of 3.33, so we need a bunch at B. 26. All right. This was some forces in the Y to get By. So on these beam problems, starting next week, actually probably starting Thursday, our goal is to get to the bending stress. We want bending stress. So to get there, we've got to be able to do a free body diagram. We've got to be able to solve for the reactions. Then we've got to be able to draw the shear diagram. Then we've got to be able to draw the moment diagram. Then we've got to be able to determine the maximum moment and then run the bending stress equation. So it's a multiple step problem with lots of opportunities to muck it up. So working in teams is good. That's why we're working in a team right now. Questions so far? No, we're good. I think this is statics, so we should all be able to do this. Maybe not error free every time, but we should get this, right? We understand that process. All right, so now the new parts. You good, Nick, with your numbers?
Yeah.
Okay. The new parts is these diagrams. The reason we try the diagrams is to find maximums. So what we're gonna want is maximum bending stress, which means we need maximum moment, right? And we're gonna want maximum shear stress, which means we need maximum shear force. So those are the two things we're gonna be searching for. And we do it with this graph because we don't want to plot points like we did in that last homework before this one, where we did the moment at 2 feet and the moment at 4 feet, right? That's too. It's too much work. We don't need to do it that way. There's a simpler way. I don't know about simpler. There's a different way that gets you to the max right away. And it's drawing the graphs. So we just have to learn how to draw these graphs. It starts with the horizontal line, and the horizontal line is as long as your beam. Right? So that's the graph. And we start with the shear diagram. And this line is the shear equals 0 diagram. So shear is this up force, down force thing, right? It's where we have down and up close to each other, and potentially it's going to shear off our beam. Normally shear is not a problem, but we always check it. Just good engineering is check it. We need the diagram because we can build the moment diagram off of the shear diagram. So we need the diagram and we need it done correctly. That's important. The way we do it is we follow the forces in the free body diagram. Literally just follow the forces. We start at the left side. The very, very left, infinitely close to AY, but not quite to it, is this 0 mark. Okay? And then at AY, we see this. Right? So we're going to move across the beam. We're just going to look at the forces and we're going to graphically represent them. So AY is how much? Wasn't it 3.33? Yeah. And which way does it go? Up. Now, the more you do this, the more you'll figure out how to kind of decide on your scale. You'll end up changing your scale all the time, but I'm gonna start with a really small 3.33. I know I'm gonna probably see 10K and a 20K, change. So I want to keep my scale pretty small. The scale doesn't matter, just try and keep it consistent. In other words, if I'm choosing this at 3, then 10 is gonna be 3 of those, right? So just keep your scale the same once you decide. Do it in pencil so you can erase it. But this is 3.33K. Because the shear diagram is force. This is kips, right? And we're just following the forces that exist on the beam. It went up 3 because this is up 3.33. Good? Now what's happening? The distribution is going which way? Down. In every foot, how much? 1 kip. So 1 foot over, let's say in here somewhere, what's my number? Yeah, 2.33. 2 foot over, what's my number? 1.33. It's coming down the same amount every foot. Agreed? It's a uniform distribution. It's a horizontal straight line. It is a uniform distribution. That's gonna make some kind of a straight line. So we put it in until it comes to another force, By. Right here is where that uniform distribution gets disrupted. So again, we're just following the forces. Notice I just ignored the 20 because we don't want to use that in our shear diagram. We don't want to use our concentration. We use that for the statics part, but we don't want to use it for the strengths part. We want to use the distribution. So at this distance, how much did it fall? Yeah, 12 kips. So what's this number?
Actually, 8.66.
Yes, somebody needs to do the math. Yep.
8.86.
Yeah, so it's 12 minus 3.33333.
8.67.
8.66 repeating. And it's negative. It went negative. Right? Everyone see where I got that?
It's just because it's 12 feet.
That's because it's, and I stopped it because By is gonna impact this situation. So you do the distribution until you come to another force on the beam, and then you're gonna stop that distribution. Because now what do I see right here?
Oh, but you didn't stop it.
Now, remember, we don't use the 20 in the strengths part. We only use the 20 in the statics. But now we're doing strength materials and the shear diagram. Don't use the concentrations. Go back to the distributions for sure. Okay? What was By equal to? Which way does By go? Up. Yeah, and I even missed my scale because this should go way the heck up there, but I'm gonna stop it right there. So it goes up a total of 26.66. So what's my number here? Seventeen nines is what I get.
And that's 26.
Wish that wasn't so close. And it's positive, right? Yeah.
And how'd you get that?
How did we get that? Good question. We're at 8.66. And then what's it C? C is up 26.66. So you need the difference between 26.66 and 8.66. And if you hit the, just hit a bunch of decimals, I get 17.99999, right? Now what happens? What do we see now? Heading away this way, what do we see? Yeah, we see our distribution coming down again. We go down a kip for every foot, correct? All the way over to the end here, what is it right there? So it's down 8 kips. Yep.
Why is it 8 kips if it's 10K?
It's not, we have not seen the 10K yet. We're doing this, we're going from here to here. All the way to it, but not quite to it yet. Infinite, they say, infinitely close to the 10K, but not quite to it yet. Right? So we're gonna pick up all of this distribution, which is how much? 1 kip per foot, 8 feet, 8 kips, yep. So we drop down 8 and we get what? 9.999. Repeating. Yep. And then we see the 10K and we go to 0. If your shear diagram returns to 0, you've done it correctly. Both ends need to be 0 of a simply supported beam. And a simply supported beam means nothing's fixed. There's no fixed part of it. If you have a fixed beam, like a cantilever beam, then it can support a shear force at that fixed point. So it's going to have a shear load on it. A simply supported beam, which means knife edge or pin and rollers, they will always return to 0 at the ends. Cool? That's how you know you've done it right, when you get that to come out to 0. So there it is, our shear diagram. What we want to know from the shear diagram is what's the maximum shear force? And that can be positive or negative. So we're just looking for the absolute value, the biggest number possible in the graph. What is it? That's the number we will use to calculate shear stress, to check and see if the beam is okay. Cool? Now we have a much harder situation to deal with, which is the moment diagram. First, let's let that settle in, and if there's any questions. If something wasn't clear, what is it, and can I help? Or do you see where I got it all? The first shear diagram, that's kind of exciting, I tell you. This is like, I use this not every day, but I use it on every project I do. Right? This is how you determine if your beam is safe or not. Like, this is what you do. Super important parts of the shear diagram: maximum, which we just got, zeros. If there are zeros in the shear diagram, right there, V equals 0. Right here, V equals 0. Right? Where it crosses, wherever the shear diagram crosses 0, maximum M occurs. The maximum moment occurs where the shear goes to 0. So that's super important for us. Because our next step is, hey, where's the max moment at? Well, it's right here, and it's right here. Right? They say maximum or minimums because it's the same situation. It can be a negative moment or a positive moment. We really don't care. We just need the biggest moment. So this could be a maximum or a minimum. This could be a maximum or a minimum. Okay. So those are points that we're very interested in. Are we good? Ready for the moment diagram? This will blow your socks off a little bit because this would not be a beginner moment diagram. This would be a little bit of a more advanced moment diagram. But I'm like, heck, my students are solid. They can do this. Same thing, starts with a straight line. The length of the beam. It is your m equals 0. So there's clues in your moment diagram. These are a couple clues. Maximum, minimum occur here. Right? Positive shear areas are important. Negative shear areas are important. Positive shear areas, it's good to note them. Everyone see how I'm getting that? Area down here is negative. Area above is positive. Yeah? Okay. The elastic curve is interesting and important to think about. So do you remember what the elastic curve was? I've only done it once, I think. It's the deflection. Yeah, it's what the beam's going to do. So this beam, it's a little advanced in that the support's not at the end, right? But what do you think it's going to do between A and B? In this region? Yeah, it's going to deflect down. Agreed? Wait. I need you to agree first, Ben. You agree with that?
I agree.
Yeah. Now what do you think it's going to happen out here? Yeah, it's going to do this.
Oh, what? Excuse me?
Well, it can't just go straight. It's going to have to find its rhythm, right?
Well, are there scenarios where the beam just,
Where the whole thing just goes down.
Yeah.
If this had no load to it,
I thought, because of the thick hips, oh, I guess it's 12, but
yeah, no, well, and the loads don't matter either. Like it could be 2 kips between A and B and then 12 out there, and it could still have some bottom deflection. It matters, this distance matters. And again, the elastic curve is essentially a guess at where the concavity is. Yeah,
Would it not be like waves kind of, because like, oh, there's a load right here, and here's the 2 points, so it's like a curve, and like same over here, there's 2 points, wait, so it's a curve of that.
I mean, I guess that makes sense.
Yeah,
There-
that's,
yeah, you never see a beam do that. Is that what you're saying, Kevin?
yeah.
Yeah, no, not gonna happen. There's nothing supporting out here.
If
Right?
there was a sport, would it be like that?
Yeah, but I don't know if we should do ifs yet, because we could go there. We could like add a bunch of stuff and go, oh, what's happening now? Yeah. Right? So we got concavity here, because there is a solid 12K in here for sure. And then there's 10K out here. You know, you always just dramatize it. It's gonna look much different than this, but approximately like this, right?
can visualize.
Yeah, it really helps because a beam that has concavity up, that's a positive moment. So a beam that deflects like this, and again, I'm exaggerating it, that is a plus moment, and a beam that deflects like this, that is a negative moment. So in this region, we should be looking for positive moment. In this region, we should be looking for negative moment. Again, thinking about the graph, because we're trying to draw this graph. That means positive moment, right? That's up in this region, because this is plus moment. and this is minus moment. Yep,
Positive going because it's like this, because it's going downwards.
so it's the rule. If the beam deflection concavity is up like this, it's positive moment. Means positive in the graph,
Oh, I didn't. see
in
that.
this region. Right? If it's concave down. So we're looking for graph here and here. Based on the elastic curve. It's not always easy to see the elastic curve, so it's just one of the clues. If you can see, like, you know, if it was a simple beam with two supports and a bunch of load down, then you know the moment's all positive. Like the entire graph would be positive, right? As things get more complicated, we can't go completely by that rule, it's just something to think about. All right. We build the moment graph from the shear diagram. Okay, this is gonna be a stretch for some of you, and others are gonna really like it because you've had calculus. We don't have to do calculus, that's the good news, but we have to think calculus. So positive shear means positive moment. Negative shear means negative moment, but we're just talking slope of the curve. So positive slope is what? How does a positive slope look? Up and to the right, like this. Everyone agree? Negative slope? Down and to the left. So we're thinking slope of the moment is gonna start positive and get less positive. Whoa. Start positive like this and then get less positive. See how my slope gets less? And then my slope is 0 here. Flat.
That's like inflection point.
Yeah. So again, you always dramatize it. This slope, since it's 3.33, is really tiny, but that's not going to help you right now if I draw it really flat, but it's really pretty flat. And then it gets flatter, like it's just super flat, right? But I'm not going to draw it that way because I want you to see the difference. I'm going to start like in here with that slope, and then 1 foot over, it's a little less, and then a little less, and then at this point, and I'm going to bring it down, it's flat. Just thinking through the slope, positive, 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 but getting less positive the whole way. Right? Now, it goes what? Negative, but just a little negative. Right? A little negative slope is like right here. And then what? A little more negative. And a little more negative, and a little more negative, all the way to here.
Can I see the first diagram of the?
We don't need it. We're building the moment right off of this. Yeah. We'll go back to that in a second. You remember these graphs? Is that what you said?
Yeah.
From when? Oh, sweet. Yeah.
Something like those.
Yeah.
So we'll talk about derivatives in a second. All right, so then what happens at this point? Holy crap, it goes a whole bunch positive, right? Positive slope, which means, boom, we're coming rocketing out of here. And then we're getting what? Less positive. And then boom, we go in. And this actually is not a tangency. In other words, it kind of goes in with some slope, right? Before it gets to 0. You guys gotta track this and then we can go back to the elastic curve. Don't get distracted. Yeah? Simple beams, the moments are zero at the end. Notice how many numbers did I write down to draw that diagram? I didn't write any numbers down to draw the diagram. You should not need numbers to draw the diagram. Okay, this one was easy with the numbers because this was so tiny. If this was bigger, then I'd have to calculate some numbers to figure out like, hey, did it cross? Doesn't always cross the zero line and go super negative. You know, this could have been up in here somewhere. So it's good to calculate numbers if you need to. Like if you're just not sure, did it cross zero or not cross zero?
The shear diagram like a curve.
Absolutely. Then it's second degree. Then it's third degree in the moment. Yep. So for you wondering about the derivative is, well, some of you won't like this, but some of you will. Uniform in the this is called the load curve, right? This right here, horizontal load curve creates slope, linear, but sloped in the shear diagram, which creates second degree parabola in the moment diagram. Right? So if we had sloped here, we're going to have second degree parabola here, we'll have third degree parabola here. If we have a parabolic curve, the second degree, then we'll have third degree here, fourth degree here. That's why in the back of the book, there's equations for nth degree parabola. So you don't have to actually calculate the area with calculus, you can use their formula.
So that's first, second, third.
Yep. Yep. Anyway, what we want to know is moment here and moment here. And just kind of based off the diagram, I'm pretty sure this is going to be our max. But it's always good practice to calculate both maximums and minimums. Okay? How do we calculate that? From the shear diagram. Area to the left of the point you're interested in will give you the moment. So, area of that triangle is that moment. Uh-oh, we have a problem. Do we know everything about that triangle? We know its height. Do we know its length?
Yeah.
This is its length right here. You tell me what that is then, because I sure don't know it.
The height would be 3.3
Yeah, we got that.
and the length would be,
With those down.
Wait, do we know it? Is the
We
question.
can find
we
it.
can figure it out.
Can we find it? Yes,
figure it
we
out.
can do anything, right? We're
Okay.
that sharp. But is it given to us?
No.
No, we have to find it. Yeah, because this moment is the area of that triangle, which is, what's the area of a triangle? 1/2 the base times the height. We need the base, x. How do we get it? Similar triangles is the easiest one. That's where we take and make a big triangle where we know everything. We know 12 feet. And we know this height from here to here. That's the part that can be tricky. It's the 866 plus the 3.33 to get the total height, right? So how do you do similar triangles? You want to remember? You set the base. I'm gonna say the base 12 feet, right? Over the height, which is what? Well, it's not 12 feet.
Like 8.
It's 866 plus 3.33 kips. So how much, what is it?
Almost.
12K? That's the first triangle, and you set it equal to the second triangle, keeping the ratio the same. So the top is X. The bottom is 3.33. So that's how you do similar triangles, and you solve for X. Anyone remember that? Probably not, but now you remember it. So what is that? 1 times 3.33? Did that algebra? I did that algebra in my head.
I do too. I was going to tell you, it's a 45 degrees angle, so it's supposed to be the same.
Yeah, it's supposed to be much steeper, but I'm not, I used the whole paper. I need a whole whiteboard. All right, so now what's my area? That what you get? Anybody else get that? 5.56?
I got 5 repeat.
I think yeah,
5.54.
that's here. So how do we get this one? Same method, but now you have a plus, because we're here, we look left, we have to do everything to the left. So we have a plus moment of 5.56 and a negative moment of this, whatever it is. So we have to calculate that, but these two, one's positive, one's negative. We know it's 866 from here to here, and now we know that this is 866, right? Repeating, same kind of thing. So we have a positive 5.56, but then we're gonna minus 1/2 8.66 8.66. This triangle. Got me a number.
5, 6.
I get 31.98.
But
Actually, I get 99, but that's probably
I
round.
get 32 even.
Yeah.
32.
And it is down here in the negative area, but again, we don't care. We just want the absolute value, the biggest moment on the graph. And that is this one by far.
Got to, what's it called, have a subtracted 5.56.
Oh yeah, you gotta take it away. Yep. Yeah, this is negative, this is positive, so this one has to be taken from the other. Good? Now we have our maximum moment and we could go for bending stress, but we're out of time, so we will do that on Thursday. You have a couple problems to do. Let's look it up. Oops. You're gonna do 13 and 16 out of chapter 13. So we just blasted into the next chapter. What did I say, 13 and 16? Yeah, so do the right ones. Yeah, and I want both shear and moment diagram, okay? Both shear and moment diagram, even though the book I think might just say complete the shear diagram, I want you to go for the moment also. Cause you're capable. It's fun stuff.
Okay. Pretty fun.
Yeah, it was hard for me to even, like, grasp or